where we can determine the possible behavior. So remember, a fixed point is something where x plus n, x of n plus 1 is equal to x of n. So we're trying to figure these things out. We're trying to figure out what are the numbers that these could be. And we saw, for instance, that let's go back and let's look at, let's change the value of alpha and see what that does to the system. So if I change the value of alpha and I set it equal to be 0.5, what it looks like is that this is being pulled towards 0. So, and you can see that visually here. When alpha equals 0.5, it looks like this is being pulled towards 0. So it looks like 0 is an attracting fixed point. Before we can determine the attracting fixed points analytically, we need to determine just what are the fixed points. So our ultimate goal is to determine if there are attracting fixed points, because that's a really important question. But to determine that, first we need to determine, are there any fixed points at all? Okay, so the way we do that is we're going to set up our equation. I know we've done this before, but we need to review it, I feel. So apologies if this is too slow, but I think it's important to do. We're going to set up x of n plus 1 is equal to 0.5 x of n times 1 minus x of n. So we're writing down our original equation. And then the key is that if this property holds that x of n plus 1 equals x of n, we can drop the n. These are the same. We can just replace both with x. And so now I have a really cool equation that will work nicely, which is x equals 0.5x times 1 minus x. So this is the equation that I need to solve. So let's try to solve it. Can you solve it? Of course you can't. This was high school. This was high school stuff that you did. You might need to do the quadratic formula. You might need to factor it. You might need to do algebra. Nobody wants to do that. So let's use Mathematica. I mean, I'm being facetious, okay? You should know how to solve this, but it doesn't give us new insight to solve this equation this way, because we already know how to, and if we don't, it's unlikely to stick if we do it again. So we're going to solve it. We're going to try to solve the equation. So let me do that again then, because it's kind of important to see the whole process. So I want to solve the equation. So the way Mathematica works is it's a notebook computing environment. So when you type things in, you're inserting a cell. If you know about Jupyter Notebook, it's the same idea. If you don't, then you'll understand it better when we do Jupyter Notebook. But I'm trying to solve x is equal to 0.5 times x times 1 minus x for x. Now notice, I'm going to leave it the way I had it originally, where I made a mistake and I got an error because we miss more than we hit. And you can see these, it's showing me red things, and these red things are illustrating, hey, you have an error. And to see what the error is, you need to expand the cell. So over here, where there's this plus, you click the plus, and it tells you what the error is. And in this case, the error is really simple. I just forgot to close a parenthesis. And that's probably 50% of our errors in computing. So now I hit Shift Enter, and it tells me that I have two solutions. I have x is -1 and I have x is 0. Well, only one of these is something that I wanted to have happen. We said that our output of May's equation should be between 0.0 and 1.0. So I would be really perturbed if I got -1 here. That really isn't relevant. The relevant solution is x equals 0. And so if this is going to go to a fixed point, it needs to go to 0. Because May's equation represents a proportion of population, and you can't have -1 of a population. So hooray, we've learned how to solve an equation in Mathematica. That's pretty cool. Let's do another one. Let's see if we can figure out where does the attracting fixed point become non-zero. So in Microsoft Excel, I am going to change the alpha parameter to 1.2. And now it looks like I have an attracting fixed point. The attracting fixed point is not 0. So I would say at alpha equals 1.2, the system appears to exhibit an attracting fixed point of like 1.6 repeating roughly. So and I'm just seeing that experimentally. But in this instance, I can confirm that analytically by using Mathematica or high school algebra to solve the equation. So at alpha equals 0.2, I can solve x equal 1.2 times x times 1 minus x for x. And it tells me that there are two fixed points. This equation has two solutions, x equals 0 and x equals 1.6 repeating. But now I don't know why we wound up here and not here. But there are two fixed points. That's what the equation told me. Why is the, sorry, there's a decimal error here. This should be 0.1. Why is 0.1? And that's what we'll look at next time. So thank you for your attention. I will stick around. Here I have set the value of the alpha parameter to 3.3. And now I'm going to see what happens. So I have my two different initial values. One is in orange and one is in blue. And I'm going to make them be further apart this time. So instead of having my initial values be really far apart, I'm just going to have them have more distance between. What you see, well, I'm going to just show you the data. You show me what you see, the chart and in the pattern here. They alternate values, yeah. And in both time series, they alternate values. They alternate them differently, even or odd. But this is what's called a cycle, an attracting cycle, because the system gets sucked into this cycle. This is an attracting cycle of length 2. And it's attracting because even if you bump the starting value a little bit, you still get sucked into it. Attracting means if you bump the starting value slightly, you still see the same behavior. You know what I mean by bump? Some people get really hung up on this. You need a precise mathematical definition of bump. No, you don't. It means you just bump the value slightly, right? So you could say this qualitatively as there's an attracting cycle of length 2. And in the graph, you see that when the things are far apart, the path to the attracting cycle is different. The attracting cycle occurs either time. It occurs both ways. Does this make sense? Trust your eyes. Like, it's possible that you're being misled, but so alpha equals 3.3, there's an attracting cycle of length 2, attracting cycle of length 4. Okay, can you find an attracting cycle of length 8? Can you find an alpha value where there's an attracting cycle of length 8? So hopefully you've got your Excel up and you're experimenting and you're playing along with me, because this is no fun just to watch the instructor do. The whole point is trying to give you a tool where you can jump in and start playing with it right away, and play is the operative word. So if I give you a different system, what if I give you